Hi, everyone. We'll get started in a minute. Can you all see the whiteboard? Okay. What answers did you get for the first question? Okay, good. 140 is correct. Dhanush, can you explain?
Okay, so since one son gets 1/2 of the herd, that means that the second son and the third son and the fourth son must have the other half of the herd. So you can do like 1/4 plus 1/5 plus 7 cows equals half of the herd. So that'll be 9/20 plus 7 cows equals 10/20 because 10/20 equals 1/2. So then you can do 10/20 minus 9/20, and that equals 1/20, which equals 7 cows. So then I did 7 times 20 to get 140 cows.
Good. Yep, that's correct. So yeah, that works. Another way maybe you can also think about it is so one of the cows gets 1/2, the second son gets 1/4, and the third gets 1/5. So if you add these up, you see it's 10/20 plus 5/20 plus 4/20. So this adds up to 19/20. And so the remaining is only 1/20 of all the cows, and this is equal to 7 cows. So if 1/20 of the herd is 7 cows, the whole herd would be 7 times 20. So we get the same 140 cows as the total herd. Any questions on this? Okay, let's move on to the second question. Any answers for this one?
I am not sure about this one. Is it 49 out of 99?
That's a little higher, but maybe let's start off with thinking about, so this is actually very similar to one of the problems from from the previous week. So let's try drawing something out and then we'll see if that helps anyone. Okay, so Alex and Charlie are both choosing a number between 0 and 1. So let's draw out if Alex chooses a number between 0 and 1 and Charlie chooses a number 0 and 1. And let's draw a square corresponding to all the possibilities. So Alex is choice, let's say that's going to be on the x-axis here, or the bottom of the square. And Charlie's choice is the y-axis. And each can range from 0 to 1. Okay, so all the possibilities are represented as a point somewhere in this square. So if you look at kind of all the possible things that can happen, it would be some point on this square. So for instance, the point here would correspond to Alex and Charlie both choosing 1. This point would be Alex choosing 1, Charlie choosing 0. This would be Alex choosing 0.5, Charlie choosing 0.5, and so on. Okay, so we want the sum of the numbers not to exceed 0.5. So if Alex chooses 0, what is the maximum that Charlie can choose for this to be true? So if Alex chooses 0 and the sum shouldn't exceed 0.5, what should Charlie choose? Or what's the maximum Charlie can choose? Good, 0.5. And what point does that correspond to in this square? So that would be this point here, right? So the middle of this, yeah. On the y-axis on half, good. Yeah, so that would be this point. Okay, so let's try the other way now. So what if Charlie, we know, chooses 0? What is the maximum? So that's going to be somewhere on this line. What's the maximum Alex can choose such that this is true?
.5.
Good. And what point is that?
Half of the x-axis.
Good. Yes. So that would be this point. Okay, so now the question is, what area of this square corresponds to the sum of numbers not exceeding 0.5? So we found 2 of these points. What does the whole area look like? So think about, what if Alex chose 0.1? What's the maximum Charlie can choose? 0.4. Okay, so that would be this point here. Okay, so what is the area now? So let's try connecting all these points. So the area we're looking at now is this area. So this triangle corresponds to points where if you add up Alex and Charlie's value, it would be less than 0.5. So we saw that this point, they equals 0.5. We saw this point, they equal 0.5. And if you look at any point in between, so Alex is 0.1, Charlie would be 0.4. Alex is 0.25, Charlie would be 0.25, and so on. Okay, so now what fraction of the area of the whole square is covered in this triangle? Good, 1/8. Why is it 1/8?
Because a quarter of the square is like a miniature square and it's half the square because it's a triangle. So.
Good. Yeah, that's correct. So yeah, if we connect these two and kind of fill the square, so what we see is this square has side 1/2. So this is the square, this inner square. Let me highlight it. So this inner square here is 1/4 of the entire square. And if you look at this triangle, is clearly 1/2 of this square. So overall, this is 1/8 of the entire square. Or another way of looking at it is you can find the area of this right triangle is this side is 1/2, this side is 1/2. So base times height times 1/2. So the area of this right triangle is 1/8. So that way also works. So the entire square corresponds to all the possibilities. Any choice that Alex chooses, any choice that Charlie makes. So the total is 1. The potential area that corresponds to the sum of the numbers being less than 0.5 is this triangle, which is 1/8 of the total. So the answer here is 1/8. So the probability that the two numbers sum to less than, or the sum does not exceed 1/2 is 1/8. Any questions on this? Does anyone remember the name of the technique here? So we had a similar problem like this 2 weeks ago. Okay, the name was geometric probability. And the the reason for this is that one, we're kind of representing this pictorially, and so we're kind of using geometry to see the possibilities. And one kind of sign it would be this is when they choose a real number between 0 and 1, you can represent all the real numbers by thinking about the line between 0 and 1. So any point on that corresponds to one choice. So when you see that, this might be an indication that you might think about geometric probability. And when you have the two people, it becomes two dimensions. So Alex on one axis and Charlie on the other, and you can think about it in a kind of a two-dimensional way. Any questions on this? Okay, let's move to the third one. Any ideas on this one? Okay, good. 39 is correct. Avinash, can you explain?
I use trial and error for this, so like, I don't know if there was a systematic way to solve it. Can you
Okay.
please explain to me if there was a fast way?
Okay, sure. Trial and error works. So how did you kind of be sure that nothing larger than that didn't work?
I took multiple numbers and subtracted 11 from them until I got a number that you could divide by 5.
Okay, good. Yeah, so that does work. So let's actually look at kind of a similar method first, and then we'll talk about maybe a more efficient way of doing these kinds of questions. So we want to basically see at some point all of the numbers will be possible, and let's see why. So if we think about, so we could start from 11, right? Now we know that 11 can be made with just one pack of 11s. Now I could add a pack of 5 to this, right? So then the number 16 is possible. I could add 5 to that, the number 21 is possible. Then 26 is possible, 31 is possible, and so on. What is common about all these numbers?
They all end in 6 or 1.
Good, they all end in 6 or 1. And that's essentially equivalent to saying they have a remainder of 1 when divided by 5. Does everyone agree with that? So if a number ends in 1 or ends in 6, if I divide it by 5, there's 1 left over, right? So either if it ends in 1, when I subtract the 1 out, it ends in 10. If it ends in a 6, I subtract 1, it ends in 5, so it's clearly divisible by 5. So all of these numbers are possible. So we know what this tells us is if it ends in a 1 or a 6 and it's greater than 11, it can be purchased exactly, right? So this helps us eliminate some numbers out, right? So we're trying to look for what is the largest number of jamuns that cannot be purchased exactly. Okay, so we've started with 11 and we keep adding 5s. Actually, let's even cover one step before this is just 5, 10, 15, 20, and so on. So what is the commonality of these numbers?
They all end in a 5 or 0.
Good. They all end in a 5 or 0. And can we write it the same way as we wrote the second one? So we wrote it as remainder of 1 when divided by 5. What would it be for this sequence?
There would be no remainder.
Yeah, so remainder of 0 when divided by 5. So I'll write it in this way, but this is also, if anyone is familiar with mod or modular arithmetic, you can also write it as 0 mod 5 or 1 mod 5, but that's just saying the same thing. So when I divide by 5, there's no remainder. And that's kind of a helpful notation, but it's not kind of needed. You can kind of just express it in this way. Okay, so we've covered some of them. So we know, okay, all the numbers divisible by 5, all can be made. If I have a remainder of 1, I could put 111 and then keep adding 5s. Okay, so the next one, let's start with 22. Then we'll add another 5, 27, 32, 37, 42. So all of these are possible, right? I start with two 11s. I add a 5, I add another 5, I add another 5, I add another 5. So all of these are also possible. What is true about these?
They all end in a 2 or 7.
Good. Can we write it in the same way?
It would be like if divisible by 2 would have mod 5, or all the way around. So remainder of 2.
Good. Yeah. So remainder of 2 when divided by 5 in the mod notation, this would be 2 mod 5. Okay, so the next set we'll do 33. So we're basically thinking about, let's start with some packs of 11s, and then say if we keep adding 5s, what is kind of the sequence I can make? So now 33, what does this sequence look like? Okay, so what's common here?
Remainder of 3 when divided by 5.
Okay, and what is my last sequence going to be?
34, 39, 40, and onwards.
Close. Is it 34 or something else?
No, 30, 39, 34, 39, and onwards adding 5.
Close. Yeah, it should just be 44, right? So 4 times 11.
Oh, yeah.
40, good. Yeah, 49, 44, 49, 54, 59, and so on. So what is true here?
The remainder is always 4 when divided by 5.
Okay, so let's just quickly note, so all of these are possible kind of combinations, right? So these are all the numbers we can make with 5s and 11s. So can we use this information to figure out the maximum number that cannot be purchased exactly? So right now we're looking at the ones that we can, but is this useful to find the maximum that we cannot purchase exactly? Particularly, does this help us know, is the maximum actually have a remainder of 0, 1, 2, 3, or 4? Okay, so we know that if I have a remainder of 0 when divided by 5, any of these numbers will work, right? So for instance, the maximum that cannot be made cannot be 25, right? Because that's already covered here. But I know that when it has a remainder of 1 divided by 5, it starts only from 11, right? So can I actually make 6 here? Is it possible to have made 6? Okay, so how would we make 6?
6 can't be found, can't be purchased exactly because if you subtract 5 from it, you get 1. It's
Good.
a remainder of 1.
Good. Yeah. So 6 cannot be purchased, right? So if we look at this, essentially the numbers with the remainder of 1 when divided by 5, I can only produce them when it's 11 or higher than that. So a remainder of 1 when divided by 5, but smaller than 11, the 6 I cannot get because kind of I keep subtracting 5s, I'll never get a multiple of 11 out. So same for this 22. If it has a remainder of 2 when divided by 5, but it's smaller than 22. So that would be numbers like 2, 7, 12, 17. All of these I can't actually obtain. And I can do the same thing here for 33. What could I not actually have done? I couldn't have gotten 28. I couldn't have gotten 23. couldn't have gotten 18 or 13, 3 or 8. And for the final sequence, the numbers that I couldn't have gotten is 44 minus 5, so 39, 34, 29, 24, and so on. So all of these numbers couldn't actually have been obtained because they're remainder of 4 when divided by 5, but the smallest one I could actually start with is 44. And I know after that, all numbers with remainder of 4 when divided by 5 are covered, remainder of 3 when divided by 5 are covered, 2, 1, and 0. So beyond this number 44, everything can be covered. So it's the numbers below 44 that are remainder of 4 when divided by 5, below 33 with this remainder, below 22 with this remainder, and so on, are the ones that I cannot actually get. So the largest one is taking this sequence and just subtracting 5 from it. So this 39 is actually not possible. And we know from this, it's the largest one that's not possible. All of these other ones would be smaller. And 39, until you kind of go 5 above that to 44, this is possible with just 11s. But below this, we can't actually get these in any way. So this kind of proves to us that 39 has to be the number. There is actually a formula to solve these kinds of questions, and it's actually often referred to as the chicken McNugget theorem. And the reason for this is there was some problem proposed in that McDonald's selling these chicken McNuggets in packs of 2 different numbers. And what is the same kind of question? What is the maximum number that cannot be purchased exactly was a problem that was posed. And this was kind of made into a general theorem. So if it's sold in packs of A and B, where A and B are relatively prime, and we'll quickly review what that means in a second, but if they're relatively prime, this maximum number that cannot be made with A and B is AB minus A minus B. So let's apply that here. What are A and B here? Five and 11. So what does AB minus A minus B give us here?
Um, 55 minus 11 minus 5 equals 39.
Good. Yeah, that's correct. And that matches what we saw before, right? So we said the answer was 39. So actually you could just do 5 times 11 minus 11 minus 5, and that gives us the answer. And I'm not going to kind of show you the exact proof for this, but the idea here is we're seeing that kind of when we started with 11, we covered some of them. 22, we covered remainder of 2. 11 times 3, we covered this. 11 times 4, we covered this. And 11 times 5 would kind of repeat back the first one, right? So this 44 was actually 11 times 5 minus 11, right? So 11 times 5 would have gone to 55, and we subtract 11, we came to 44. So that's the AB minus A part. And the minus B is because we need to go back 1 here. From the 44 works, the 39 doesn't work, right? So kind of if you think about the formula, A times B would go, we started with 11, 22, 33, 44. 11 times 5 would take us to 55, but that is already covered. We want to go back 1 row, which is subtract A. So that gets us to 44. And now we want to go back 1 here. And this is, we're counting by 5s here. So this is 39. So this is AB minus A minus B. Okay, so this is the formula. One question, why do we need the relatively prime here? Why is this important? So let's say we have the numbers 4 and 8. So if I sell these jamuns in packs of 4 and packs of 8, is there an answer to this question? Good. Why not? So the problem is that both of these are multiples of 4, right? So there's no way to get an odd number here. If I wanted to make 7 and I can only have packs of 4 and 8, the numbers I'll make will always be even, right? There's no way to make an odd number. So there's no maximum number that cannot be purchased exactly. Yeah, I could just make any odd number and it could be extremely large, right? So this question kind of doesn't work if these two numbers have some common factor. If they do, then everything I make will have to have some common that will be divisible by that number. And I can't make anything that's not divisible by that number. So that's why you need this additional kind of constraint that A and B are relatively prime, which basically means that A and B don't have any common factor other than 1. So if they're both divisible by 4, then all the things I can make are divisible by 4. So I can't really solve the question. But if I can solve the question and the two numbers are relatively prime, then it'll always be this number, AB minus A minus B. Any questions on this? Okay, that's it for today's class then. We'll see you all next week.
Thank you.
Thank you.